Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In our previous videos, that is Polymer 1, we were discussing about polymer, what are its type, classifications of polymers under different category, and we have just started off with the preparation of polymers and their uses. So the first polymer which we had dealt is low density polyethylene, that is LDP. Okay, and now further we will be continuing with high density polyethylene. So basically both both the polymers are of that polymer of ethene itself, but the only difference is the packing in the linear chain. If I am saying LDP, that is low density polyethylene, what's the difference? The low density polyethylene, in the low density polyethylene, the polymer chains are placed at a distance, as a result of which the volume increases and density decreases. Hence the name low density polyethylene. Okay. Now, if I say high density polyethylene, what happens? The linear polymer chains, they are very closely packed, as a result of which what happens? The density is higher as compared to LDP. Okay. So, if we see the preparation and properties, we know obviously high density polyethylene is a polymer of ethene only. So, here we have taken n number of ethene molecules. Okay. This is the monomeric unit. This is the monomer. Okay, monomer means the smallest part. Okay, the smallest part of the or the smallest unit of the polymeric chain. So here what happens? The monomeric unit is ethene. When n number of ethene, they are joined end to end, they form a polymeric chain. We call it polyethene, right? Now, when these linear polymeric chain, they are placed very close to each other, as a result of which what happens? The density increases, and hence we call it high density polyethylene. Okay. So, when ethene reacts at a temperature of 333 Kelvin to 343 Kelvin in the presence of at 6 to 7 atmospheric pressure, in the presence of a catalyst called as Ziegler-Natta catalyst. Note the difference. In the low density or the LDP, we were not using any catalyst, but in the HDP we introduced a catalyst which is Ziegler-Natta catalyst, and it is basically a zinc based catalyst. The central metal of this catalyst is a zinc. Okay, the central metal is zinc. So this is the Ziegler-Natta catalyst. In the presence of this Ziegler-Natta catalyst, monomer ethene, they polymerize together by breaking of this pi bond. This pi bond basically breaks, as a result of which, this pi bond breaks, as a result of which the linear chains of ethene are formed, which we call polyethylene. Now it has high density due to close packing of the polymeric chain. Okay, close packing of the polymeric chain. It is also chemically inert, tougher and harder. Obviously, density increases, closely packed. So, it is chemically inert, tough and harder. Uses: it is used in making containers, housewares, bottles, toys, electric insulators, etc. Why insulators? Because polymers are basically chemically inert. Okay, they are not that reactive, they are not at all reactive. So, we use this for any chemical reactions or any insulation process. Okay. So, I hope you are clear with this. High density polyethylene, the monomeric unit is ethene itself, and the only difference is here we are using a catalyst which we call Ziegler-Natta catalyst. In the presence of the Ziegler-Natta catalyst, it polymerizes to form polyethylene, which we call high density polyethylene, because the chains are closely, linear chains are closely packed. Okay. They have high density due to close packing. It is also chemically inert, tougher and harder. Okay. And you have to note the uses here, used in making housewares, bottles, toys, electric insulators, etc. Okay. Moving on. Okay. We have polyvinyl chloride. So I guess you must be familiar with this word, polyvinyl chlorides. Basically in TV ads and all, you might have heard about PVC pipes. Okay, so polyvinyl chloride is a polymer of vinyl chloride, which is basically used in the pipes of the, used in making pipes we use in our buildings, right, for construction and all. So, polyvinyl chloride undergoes polymerization in the presence of a small quantity of benzoyl peroxide. Okay, Now benzyl peroxide acts as an initiator for the reaction. Initiator, that means it starts the reaction, it initiates the reaction. Okay, so benzoyl peroxide basically acts as an initiator for the reaction. So when vinyl chloride undergoes polymerization in the presence of a small quantity of benzyl peroxide, polyvinyl chloride is formed, right? So I hope you can see the reaction where n number of vinyl chloride, which is the monomer, when n number of vinyl chloride, they are polymerized in the presence of benzoyl peroxide, polymerization takes place to form PVC, polyvinyl chloride. Okay, you have to remember the structure of vinyl chloride. What are the uses? It is used for making sheets for tank lining, safety helmets. Okay, used for making safety helmets, refrigerator components, tires, cycle and motorcycle mudguards, raincoat packing, tablecloth, electrical insulators and chemical containers as well. Okay, so these are the uses of PVC, right? Moving on, we have bakelite, and bakelite is otherwise called as phenol formaldehyde resin. Basically, resin is a resinous or gummy substance, right? So bakelite is that kind of a substance which is formed by phenol and formaldehyde. When phenol and formaldehyde react together, they form two isomers. Okay, one is orthohydroxy, which one is orthohydroxymethylphenol and para-hydroxymethylphenol. See, this is the phenol. This is formaldehyde. When phenol and formaldehyde react together in the presence of any basic catalyst, they give rise to orthohydroxymethylphenol plus a para isomer which is para-hydroxymethylphenol. Now, if I polymerize only the orthohydroxymethylphenol, I will get a new polymer which is called novolac. Okay, it is called novolac. It is a linear polymer. Okay, linear polymer of orthohydroxymethylphenol. Okay, it is a linear polymer of orthohydroxymethylphenol. Now, when the orthohydroxymethylphenol thus formed undergoes polymerization with phenol to form a linear polymer compound called novolac. Okay, this linear polymer compound is called novolac. But when I polymerize ortho as well as para isomers together, the polymeric chain so formed, it is basically a cross-linked polymer, and that cross-linked polymer is called as bakelite. Okay, the cross-linked polymer of orthohydroxymethylphenol and para-hydroxymethylphenol is called as bakelite. So if I compare orthohydroxymethylphenol and if I compare novolac and bakelite, so how can you imagine what will be the strength, difference in strength in both novolac and bakelite? Obviously, novolac is a straight linear chain polymer, while bakelite is a cross-linked polymer. So cross-link means there is development or there is presence of an additional bond, and that additional bond adds up to the strength of that substance, right? If bakelite is having an additional bond in itself, then obviously bakelite will be coming out more stronger as compared to novolac, which is otherwise made up of only linear chain polymers. Okay, understood? So I can say bakelite is strong as compared to novolac. Okay, if I compare the strength, then bakelite is strong as compared to novolac. Now if I move on, what are the uses of it? Uses of bakelite: it is used as electrical insulators in plugs and switches, cabinets for TV and radio, telephonic parts, paints and varnishes, and basically very important thing to remember is it is used for softening hard water. What is hard water? Basically, hard water consists of salts of calcium and magnesium, as a result of which they do not foam with detergent or soap. So what basically bakelite does is it softens the hard water. Okay, it makes the hard water fit for use by converting it to soft water. Okay. Now we have the next polymer, which is rubber. Okay, rubber is a naturally occurring polymer. It is obtained as latex from rubber trees. It is highly elastic. It is easily deformed but regains its original shape after the stress is relieved. Obviously, we have all seen rubber, right? If you pull the rubber, it elongates, and we leave it, it comes back to its original shape. Okay, so when stress is removed, it regains its original shape. So rubber is obtained from rubber plants like Hevea brasiliensis, generally found in the tropical region of Brazil, Indonesia and Malaysia. Certain saps are cut on the rubber plants. Saps are cut down, and the thick milky liquid that comes out is called as latex. Okay, we cut out the sap of the plant, and a thick liquid comes out, which we call latex. This latex is then extracted. It is diluted with water and filtered to remove any impurities present in it. Okay. Then the latex is treated with acetic acid, vinegar, which we call. Okay, the latex is treated with acetic acid or vinegar, CH3COH, which coagulates the latex. The coagulated latex is then passed through a creeping machine to obtain sheets of rubber. Okay, they are passed on to a creeping machine where fine sheets of rubber are extracted. These sheets of rubber are then put into molding machine to get molded articles. Okay, that's how we extract natural rubber from the plant. This is basically the process. Now, rubber is basically consisting of a monomeric unit called isoprene. Okay, the monomeric unit of rubber is isoprene. So, a polymer of isoprene will be polyisoprene, and it is a cis isoprene. We have two configuration. One is the cis configuration and there is a trans configuration. So, natural rubber is basically a cis isomer. So, it is called as poly-cis isoprene. Rubber is a monomer of polymer of monomeric unit called isoprene, and hence the name poly-cis isoprene. Now, if I see, this is the structure of isoprene. CH2 double bond CH, C double bond CH2, and to the second carbon there is a CH3 attached. Okay, this monomeric unit, it polymerizes. How does it do that? This bond, basically this double bond breaks, and as these both carbon atoms, this carbon atom and this carbon atom will elongate their bond, right? But these two carbon atoms, they do not have any like chains or branches, they cannot complete its octet. So in order to complete its octet, what happened, what they do is they form double bond among themselves. This is what happens basically. Okay, so this is how a natural rubber is, a polymer of natural rubber is formed. Now, what are the drawbacks of natural rubber? You have seen when the rubber is placed, mostly in summers also, if the rubber is placed outside, when we touch that rubber, it becomes very sticky, a slimy substance is like developed on the top coating of the rubber. Right? Why? What does that happen? Because rubber has very less thermal stability. It is very less heat resistant. Okay, that makes it very unfit for normal use. So natural rubber has the following drawbacks. It has very low thermal stability, very low tensile strength. If you pull the rubber, it will stretch, but after a certain limit, it will break. Right? It will break off. So, it has very low tensile strength, it has high water absorption capacity, it is attacked by atmospheric oxygen and ozone. These are the drawbacks of rubber which makes it unfit for use. Okay. So, in order to make it more user friendly, what we do, we implement a method called vulcanization. Okay. We use a method called vulcanization of rubber. So, basically what we do in vulcanization is we react the rubber with some sulfur or sulfur containing compounds at very high temperature, that is 1000 to 140 degrees, okay, degree Celsius. So basically we heat that, we react the rubber as well as sulfur. As a result, rubber is initially in its raw form, it is linear chain, right? But when it reacts with sulfur, cross links starts developing. The sulfur forms cross link between two rubber chains. As a result of it, what happens? The cross links adds on to the extra strength of the rubber. As a result of which, what happens? Its thermal stability, basically all the physical and chemical properties a substance undergoes or shows is basically due to its bonding or the structure, right? So if we improve upon the structure, if we work on the structure, then the durability or the quality of the substance will also improve. So if you are reacting rubber with any sulfur containing compounds, then what happens? Cross linking starts developing, and due to those cross linking, the strength of the rubber improves, the rubber becomes more stronger and harder, and all the drawbacks of the natural rubber, they are basically omitted. So if we see, natural rubber is a thermoplastic. It has no cross links between the polymer chain. It becomes soft and sticky when heated. It is not hard and tough. We have seen in the drawbacks. The properties of natural rubber can be modified and improved by the process of vulcanization. Okay. To improve the properties of natural rubber, it is heated with sulfur or sulfur containing compounds at a temperature of 1000 to 1400 degrees Celsius. The chemical process in which natural rubber is heated with 4 to 6% sulfur or sulfur containing compounds with a view to overcome the drawbacks of natural rubber. What was the main motive behind this? It is to improve the quality of the natural rubber. So this process is called vulcanization. Okay. Now see, this is the reaction of vulcanization. During vulcanization, sulfur crosslinks are formed between the layers of polyisoprene at the carbon atom containing double bond. The formation of crosslinks makes rubber hard, tough with greater tensile strength. Although natural rubber is thermoplastic substance, yet on vulcanization it is set into a given shape which is retained. It is basically, it becomes hardened. Okay. The properties or the drawbacks of the natural rubber are overcome. Got it? So, sorry. Yeah, what are the advantages of vulcanization? After vulcanization, almost all the drawbacks of raw rubber are eliminated. Now, vulcanized rubber has high thermal stability, has comparatively lower tensile strength, has lower water absorbing capacity. It is not attacked by atmospheric oxygen or ozone, and it is resistant to acids as well as alkalis too. Now, here I have attached an image of how a natural rubber and a vulcanized rubber looks. These black dots basically represents the cross linking or the sulfur linkage, which adds on to the strength of the vulcanized rubber. Okay. So this brings us to the end of the module of polymers. I hope you are clear with the chapter. All you have to remember in this chapter are the preparation as well as uses of the polymer and the monomeric units. So that's all for the video. Thank you so much.